welcome to the deep dive. Today we're jumping into discrete geometry to look at something really elegant, Helly's theorem. It's all about these things called convex sets and, well, how they intersect. We want to give you a quick way to get up to speed on this.
Yeah, it's a great topic. Helly's theorem looks simple, maybe, but it's really a cornerstone. It gives us some deep insights into geometric structures, shows how simple local things can imply something big globally.
And the backstory is pretty interesting, too. Edward Helly found it way back in 1913, but he didn't actually publish it himself until 1923, a whole decade later. And by that time, other folks, like Radon in 21 and König in 22, had already published their own proofs.
Right, exactly. So Helly's own proof came out after others were already known. A bit of a historical quirk.
Okay, so let's unpack the main idea. Helly's theorem for, finite collections. First off, maybe quickly, what's a convex set?
Good place to start. Basically, a convex set is any shape where if you pick any 2 points inside it, the straight line connecting them stays completely inside the shape. So no dents, no holes. Think like a perfect circle or a triangle, a solid cube.
Got it. Solid, kind of bulging shapes.
Yeah.
Okay, now the theorem. Imagine you have a bunch of these convex shapes, say n of them, in d-dimensional space, our day, right? Like 2D for a screen, 3D for our world, maybe even higher dimensions for complex data.
Exactly. So here's the core idea. If
Right.
you have n of these sets, and n is at least d plus 1, so on a flat surface, d2, you need at least 2 plus 1 equals 3 sets. And here's the condition. If every possible smaller group of exactly d plus 1 sets has a non-empty intersection, meaning they all share at least one common point, then the theorem guarantees that the entire collection, all n sets, must also have a common point, a non-empty intersection for all of them together.
Right. That's the leap that feels surprising. You check these smaller groups, these d plus 1 groups, and if they all overlap, then everything overlaps globally. Why isn't that just obvious? Why might we think they wouldn't all intersect?
Well, our intuition can stumble a bit, especially in higher dimensions or just with lots of shapes. Think about, dozens of overlapping circles on a table, even if every group of 3 touches somewhere. It kind of feels like maybe the whole stack wouldn't necessarily have one point common to all of them. But Helly's theorem says, nope, it has to. It's a really powerful insight. And it was so foundational, it actually led to this whole mathematical idea called a Helly family.
A Helly family. What does that mean?
Essentially, it's a classification. Mathematicians started looking for other types of objects, not just convex sets that have the same property, where local intersection properties guarantee a global intersection. It shows how one core theorem can open up new research areas.
That makes sense. And I think it's cool how these ideas connect. Like, this isn't just pulled out of thin air. The proof for the finite version uses another important result, right? Radon's theorem.
Indeed. Radon's theorem is often used in the proof. It deals with partitioning points in a way that basically helps break down the Helly problem into manageable pieces. It's like using a specific mathematical tool to build the larger argument. Shows how results build on each other.
Right, connects the dots. Okay, thinking bigger picture, Helly's theorem didn't just stop there. It has extensions, right? You mentioned the colorful Helly theorem.
Yes. The colorful Helly is a really neat variation. Instead of one big collection, you have d plus 1 different collections. Let's call them colors. So you have, say, a red collection, a blue, a green, and so on, up to d plus 1 colors. The theorem says, if every combination you can make by picking one set from each color has a common intersection point.
Picking one of each color, like a rainbow combination?
Exactly. If every rainbow choice intersects, then the theorem guarantees that at least one of the original single-color collections, like all the red sets or all the blue sets, must itself have a common intersection.
Wow, okay. So if the mixed groups always intersect, then at least one of the original pure color groups must intersect internally? That's quite a twist.
It is, isn't it? And there's also the fractional Helly theorem. This one shifts things a bit towards probability or proportions. It says something like, if a certain fraction of your possible d plus 1 size subgroups intersect, then you're guaranteed that at least some positive fraction of the total collection must also intersect. It deals with how much intersection you have.
Which sounds really useful for areas where things aren't always certain, like optimization or maybe data analysis.
Precisely. It finds applications in combinatorial optimization, computational geometry, areas where you're dealing with large systems and guarantees about portions of them.
So wrapping this up for you, the listener, Helly's theorem is this really elegant piece of mathematics. It's simple to state, but it reveals something deep about how shapes interact, especially convex ones. Its legacy is pretty significant in discrete geometry.
And maybe a final thought. Appreciating theorems like Helly's, these sort of elegant truths, can change how you look at complex information generally. It encourages you to look for underlying structures, those simple conditions that might lead to a bigger picture understanding rather than just seeing a lot of noise. Look for the connections.